Welcome to Industrial PLC Applications Level 2. This is a review of timers and counters. This review will focus on on-delay timers. After completing this video, you should be able to identify an on-delay, off-delay timer instruction called a TONOFF. You should be able to add a TONOFF to a connected components workbench project, explain the TONOFF's operations and limitations, and explains its preference over free-running timers. In industry, warning lights and horns notify personnel of a change in operational state or emergency. The two flashing lights have different intervals of off and on. With older mechanical strobes, you were limited and you could only use a steady beat. With PLCs, that changed. When flashers were first set up in PLCs, they were set up as a free-running timer, and it was used to get an output to flash on and off. As you can see from the example, you take the normally off contact, and you're using that to trigger the input of our timer. When the timer is finished, the cue gets set, and the not becomes false, therefore the timer turns off and the process is reset. So a free running timer was one where the not done Q bit in this case was placed in front of the timer instruction. When they first came out, you could only set the time in 1 second increments. But older PLCs are considerably slower than today's versions, and the speed of the processor killed the free running timer since it updates faster than the logic can follow. Okay, so we have the TON_1.Q triggering the TO1 itself. Since it's the examine if open, that means it's not done. Just go ahead and let it count, and when the 5 seconds are up, it'll be done, and then that'll open the circuit up and it should continually reset itself. But as you'll notice, the output from that instruction never turns on, and it's simply because the processor is running so fast that the moment that output becomes true, it resets itself and carries on again. And that has a lot to do with the processor's speed, whereas before, when they had only two choices of 100 milliseconds or 1 second, the scan time was much slower, and you could use a 1 second flasher or a 5 second flasher and it would repeat constantly. But here, because the processors are so fast now, the free running timer is deceased. The other problem with free-running timers of old was that it was limited in its behavior. You could not program the on or off cycles independently. To solve both of these problems, the on-delay, off-delay timer was created, the TONOFF. The TON-OFF instruction is primarily used to create a strobe signal or flasher. Since it does double duty, it has more parameters than a simple TON or TOFF instruction. Let's look at the programming parameters that you have on a TONOFF instruction. This particular example is using TONOFF_1, which is the default for when you first install any timer. They'll use that _1. So with the TONOFF_1.in, it's as it is before. It's the input that will trigger the instruction. The TONOFF_1.pt, as before, this is where the on-delay time setting is stored. The TONOFF_1.tof is where the off-delay time is stored. The TONOFF.et is where the elapsed time count is stored. The TONOFF_1.q is, as before, the final output bit of the instruction. Notice how in the example it is used to self-trigger the instruction, just like the days of yore with the free-range timers. If the intent is to make a flasher, this must be programmed in this way. So we're going to start to program a TONOFF timer, and you can see that you'll find the instruction name within the timer counter menu selection. But before we do that, we're going to put a couple of contacts on our rung. I'm going to put a direct contact, a reverse contact, and I'm going to put an output. And then I'm going to go to my timer counter, grab TONOFF, and we'll start to program the parameters. Now you notice that the timer looks a little different, and keep in mind that this timer is a time delay and a time off delay. So it's an on delay, off delay, and the two of them work together on the same cue, which gives us that flashing component. So the first thing we'll do is we'll give this a digital input because I have the simulator handy, and I'm going to demonstrate with it. And I'm going to turn on an output so that we can see it when the simulator is running. It'll be flashing back and forth. And then I'm going to program my times. There are two different time constants that we need to program. That's the on time and then the delay time for the off. So what we're going to do is we're going to use the T hashtag like we normally do, and I'm going to make this basically a 1500 millisecond, which is a second and a half. And I'm just going to get my cap locks off. I get a little nervous when they're capitals. I like to make sure that they're lowercase. It seems to be happy with that. And then I have to do my off time. Now the nice thing about this is when we used to use a free running timer, you set your time base up and then you gave it a particular amount of time. So it could be, say, 500 milliseconds, which would be a half second or one. You were kind of limited because the off period and the on period would be exactly the same. So in this case, you can use different values. Because you are allowed to program the on time and the off delay time, you can give it two completely different times. And I'm going to use capitals on that, and I'm going to make it only 500 milliseconds for the off time. So it should be on longer and off short, on longer and off short. The ET, the elapsed time, is going to be counted up as it goes in run mode. And right now I have this one reverse contact. The one thing about this instruction, just like we did originally with in the old days, what we used to call a free running timer. And let me just kind of show you the quick comparison, because there's not much to a free running timer. You would put a TON and then you would put the contact ahead of it. There we go. That was pretty much it. That was all you had to do to create a free running timer. So when the timer was triggered, it would always be triggered because its cue is not done it initially. When the cue was finished, it would change that state and would reset the timer because it's off, and you would start the whole process again. The only problem with that, of course, is with the newer PLCs, they're so fast that you actually don't see the cue change state. So this is why this other instruction was created, to emulate what used to be a free running timer. So what we're going to do is the same idea where we've got our cue bit, the not done resetting the free running timer. We're just going to take the TONOFF _1.q, and we have it there. We can use that. There it is. I'm going to delete this rung, and now this should trigger the TONOFF. So our output, when we download those to the processor, that should start to flash at different intervals. So I've already set the simulator up, so we're going to download it. My build succeeded, so I didn't make any mistakes. Good for me. Yep. Doop 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 doop. Yes, please. Okay, so right now it's doing nothing because I haven't hit my input, my digital input 1. And let me just close the output. And you can see here, I'm going to show you the simulator. I'm going to turn the input on. And I'm now in run mode. And I'm just going to move that off to the side for a second. And you can see that the output is changing state. And it's based on, it's hard to follow the elapsed time because they're two different times and it's such a short period. But if I move the simulator so you can see the outputs up on the top there, can I get that to fit? No. Okay, I'm going to put it off to the side then. You can just see the output on the bottom. So it's staying on. It's actually staying off longer than it's staying on. So if I wanted to stay on longer, then I would reverse these two numbers. And it's until you get used to working the way you want the flasher to work, then you would make those adjustments. So what I'm going to do is I'm going to stop this. I'm going to disconnect. And just to show you, I'm going to reduce this to 500. And I'm going to increase this to 1500 and download it. And we'll watch the light reverse. In several instances, especially when you have a single output, you have one warning light. By changing the pattern of the warning light itself as to how quickly it flashes or doesn't flash can indicate something, and the immediacy of it, which really saves on your outputs and energy costs and installation. Because if you want it to flash very quickly, you could put another condition ahead of this that says, okay, when the input's true, I'm going to have a counter. If the counter's not done, then flash really fast, and when it'll count the 3 pulses from the light. When it gets to say 3, it says you're not done, resets everything again, and then it will count for 3. So you can have 1 2 3 1 2 3 1 2 3, etc. So you can really manipulate the operation of it. So let's take a look at our light, and now you can see that it's staying on 3 times as long as it's turned off. And it's just from manipulating our PT and our PTOF time. And that's basically all there is to programming a TONOFF. Now you can use the Q or you can use this output. Now it's a little interesting sidebar on that particular issue with the Q versus the output that I'm using. I'm using obviously a real world output to turn on a light. If I do that, I can then use this one timer. Because I'm controlling this, I can create a whole bunch of different programs and use this contact, that same digital output contact internally, as this would end up making this a de facto global timer. Because all timers are local to the program. You can create global timers, but it becomes difficult calling them up and making sure that you've got the correct timer. And this is a sort of a cheat. If you're only looking for whether the timer's off or on, by using the output contact in another program, you achieve the same thing. Much like its cousin, the off delay timer, this instruction seems to work in reverse. It only works, however, when there is a leading not Q. As Allen Bradley states, it's an instruction that delays turning on an output on a true rung and then delays turning off the output when the rung goes false. Notice that the number of monitored data types within the instruction has increased considerably. Not only do we have double the programmable times, we also now monitor the state of the .in in two different ways. The TONOFF_1.reg still looks for the .in to go from false to true, and when this happens, the on delay is started. Now a new contact called fetch is looking for a falling edge or a contact that was true becoming false. So the TONOFF_1.fetch looks for the .in to go back to false after being true. When this happens, the off delay assumes control of the output and it delays turning it off. In our next video, we're going to show you how to program a TP or timer pulse. Until then, thanks for watching and see you next time.